Hello everyone, today we are going to discuss how to certify the existence of Majorana fermion in some condensed matter system. Majorana fermion is its own antiparticle. It can, however, exist as a quasi-particle rather than as a fundamental particle in topological superfluids. This kind of quasi-particle is very important because of their inherent resilience to decoherence, and therefore it's considered as a potential blueprint for the topological superconductor. Here we see a sketch which which has some topological conductor. Uh, it is claimed that Majorana exists in this kind of setup. This setup is proposed and developed by Microsoft Station Q. They also claim that they can measure parity PJK between any two Majorana, for example, gamma J and gamma K. Now, for this kind of setup, there are already some experimental support that Majorana exist in this kind of setup. Among them, we can name zero bias conductance peak and Shapiro straps. However, this evidence is indirect as those evidence can be explained by other means. For example, zero bias conductance can also happen due to the impurity in superconductors. So it is still indirect and unclear what would constitute the proof of the existence of Majorana fermions of this kind of setup. We, however, take the anti-commutativity properties of Majorana parities as a smoking gun to detect Majorana quasi-particle. So how we do that? First, briefly, we discuss the setup, and then we'll discuss the assumption that we restrict on our setup. The minimal number of Majorana that we required to realize our proposed protocol is 6 Majorana. So here is a graph where each vertex representing a Majorana or claimed Majorana, and the line joining to vertex is a parities, is a claimed parity. We, however, do not consider that any of this observable as parity. Rather than, we consider them as a most general observable, that is POVM, and that's why I do not denote them as AJK rather than PJK. So our goal is to certify this operator as parity operators, not to consider them as a parity from the beginning. Okay, we take 6 agnostic operators from there and arrange them in a magic rectangle in such a way that observables in the same rows or in the same columns are compatible, so that one can measure observables in the same rows simultaneously or in the same column simultaneously. The experimentalist will prepare the state psi repeatedly and then measure any of the context from these 3 rows and 2 columns. So this is the minimal assumption we have. We do not assume any other assumption regarding the initial state or the 6 operators or the Hilbert space. In particular, we want to emphasize that we do not restrict the dimension of the Hilbert space, and also we do not consider that the Hilbert space is a tensor product Hilbert tensor product subspace. Now we have all the assumption and setup. Now what's our result? Based on this assumption and experimental statistics, one can easily certify the parity operators and their state. Let's say we have the ideal statistics. What is the ideal statistics? Let's say someone measuring this magic rectangle and then calculated the expectation value each of the context. Now in the ideal case, you will have odd number of -1 for the expectation value among these expectation values, and rest of the expectation values are +1. Okay, so you will have either 1 - 1, 4 + 1, 3 - 1, 2 + 1, or all of them are -1. All these contexts are giving -1. So there will be, the thing is, there will be, if there are odd number of -1 and even number of +1, then this is giving some ideal statistics. So if the experimental is having some ideal statistics, what does this refer? It refers that there exists a 4-dimensional tensor product subspace that is invariant under the action of any of these operators. And also in this 4-dimensional subspace, Majorana Paities, the claimed Majorana Paities, anti-commute when they share a common vertex, as expected. That is the smoking gun of Majorana existence. Now, using this anti-commutativity, one can represent these operators as a 2-qubit Pauli operators, and in that representation, the state is a valid state. Great. However, in the real experiment, there can be certain error. Let's say we have a epsilon error in the expectation values. Then what can we say? In such case, the existence of a 4-dimensional invariant subspace is not confirmed. We also cannot say that the operators sharing a common vertex anti-commute perfectly. So what can we say for the imperfect statistics? For imperfect statistics, we derive that analytically the error bound for the fidelity of the state and for the operators is linear in epsilon. That is very good because it means that if there are a very small error in the experimental statistics, it means that the state and the observables should be very close to the ideal one. Okay, now how to interpret this result for an experiment? Let's talk about particular experimental setup. It's a hypothetical experimental setup where we have a quantum dot to measure parities and have 6 Majorana, 0 mode. The actual realization may be much more complex than this one. For example, there can be more than one quantum dot. Now, the experimentalist had the experimental setup, then he prepared the state psi repeatedly, and each time he prepared the state, he also measured one of the contexts. He repeat this state preparation and measurement for several times. And after a long time, he calculate, using his experimental result, he will calculate the probability distribution of the context. And from there, he can also calculate the expectation value of each of the context. And it's clear that each of the row will give +1 for the expectation value, and for the column, first one and the second one giving a +1 where the third where the expectation value for the third column is -1. Now this is an ideal case. For the, as I said earlier, for the practical case, there can be very small error if Majorana exists. Now, using this expectation value, the experimentalist can calculate the entanglement weakness for the ideal case, which is +5. And if there are some imperfectness, it's close to 5. That's pretty good, as I said earlier. But if it is smaller than or equal to 3, then that means it's in some classical state. So the existence of Majorana is not confirmed. Thank you everyone for listening to me.